Okay, welcome to pre-calculus. I apologise, we're going to rush through quite a lot of material here and only really look at it from a mechanical perspective. When we get back into class together, we'll take a little bit more time to discuss the conceptual ideas. What I'd like you to do right now is take a quick look at the do now. So pause here, have a go, and then check your answers with me on the following page. Okay, hopefully you managed to achieve the following answers. I'm not going to spend much time going through these here now, but we will just take a moment to pause, read through the first notes, and then we'll have a look at example one together. Alright, here we are at example one. How many different four-digit numbers can be formed under the following conditions? If you want to pause and have a go yourself, you're most welcome to. I'm going to begin to go through them now. If we take a look at the first constraint, the leading coefficient is not 0. If the leading coefficient is not 0, then we have only 9 options available to us. The second digit can be any one of the 10 digits from 0 through to 9, so we have 10 options here, 10 options here, and 10 options here. So in total, multiply those all together, we have 9,000 options as our possibilities. If the leading digit is not 0 and there are no repeating digits, then we can go ahead and set out those 4 digits. And there are no repeating digits and the leading digit is not 0. That gives us 9 options here. Now 0 can be included in this second digit, but we cannot have any repeats, so we've only got 9 options. Then we'll have 8 options and then 7 options. If the leading digit is not 0 and the number is even, well, let's first of all deal with that constraint of even. There are 5 even numbers, so we've got to finish with an even. The leading digit cannot be 0, so we've got 9 options here. We are allowed to have repeating digits. It doesn't say that we can't, so here's our option. That's for part C. We'll just go ahead and multiply those numbers together. And then finally, for the last part, the leading digit is not 0 and the number is less than 5,000. If we're going to be less than 5,000, then the first number can be any number from 1, 2, 3, or 4. So we've got 4 options. The leading digit is not 0 is the only constraint, aside from the fact that it's less than 5,000. So we can have 10 options in here. Okay, pause for a second, have a read through the next section of the notes, and we'll check in with one another in example 2. So here we're taking a look at the way in which the letters in the word English can be organized if we are considering 4-letter arrangements. So if letters can be repeated, we've got 4 options here that we need to go ahead and fill. In the word English, we have 2, 4, 6, 7 options. And so if letters can be repeated, we've simply got 7 options for each of those 4 letters. So 7 to the power of 4 is our answer. If no letters are to be repeated, then again you've got 4 spaces here, 7 options for the first letter. Once one letter's been used, you've only got 6 left, then 5, and then 4. You can actually represent that in factorial notation. One way to represent that in factorial notation is to say 7 factorial divided by 3 factorial. Just double check that for yourselves. You'll see that cancels to give exactly the same thing. For part C, if no letters are repeated and the first letter must be an E, then for part C here, the first letter must be an E. It means that we've only got 1 option there. Once we've got if no letters are to be repeated, we've got 6 options here, 5 options here, and 4 options here. We can write that as 6 factorial divided by 3 factorial. No letters are to be repeated and the word must contain G. So if the word must contain the letter G, how are we going to go ahead and deal with that? I want you to pause and just have an attempt at that yourselves. So hopefully you decided to set things up as follows. If we imagined that the first letter was the letter G, then the problem is very, very similar to the problem that we previously saw. However, that letter G could actually appear in any one of the 4 locations. So, for example, we could have had the letter G appear as the second letter. We would have had 6 options for the first, we would have then had 5 options here, and we would have had 4 options here. So actually, that process can be repeated 4 different times, and so perhaps the easiest way to kind of go ahead and simplify that is to say 4 multiplied by 6 factorial over 3 factorial. Alright, for the last example, no letters are repeated, and the first and last letters must be vowels. What we've got to do there is take a look at how many vowels we actually have. So in English we have 1, 2, only 2 vowels. And so we've got 4 letters here. We've got 2 options for the vowel in the first position. Once one of those has been selected, we've only got 1 option here at the rear end. We've used 2 of our letters, meaning we've got 5 letters left over. So 5 options and 4 options are here. Multiply that together. See what we get. You should get a grand total of 40 different options. Alright, here with question 3, we've got an internet site's access code, and we know that it consists of 3 digits. Not only do we know that it consists of 3 digits, we actually know what those digits are. They're 3, 5, and 7. Joe could not remember this particular access code, but he knows that the access code must be entered with the digits in the right order. How do we list all the possible arrangements? This is really just a case of being systematic. So if we start with 3, one option would then be to have 5 and 7. If we start with 3, we could have 7 and 5. If we started with 5, we could have had 3 and 7. Likewise, we could have 5 followed by 7 and then 3. We could have also started with 7, 5 and 3, and 7, 3 and 5. So what you'll notice there is that we've got 6 options. And in general, if you've got 3 spots to fill, and there were 3 options for number 1, no options were to be repeated, that would mean that you would have 2 options for number 2, leaving you with 1 final option for the last position. That's really 3 factorial, which is equivalent to 6. So just wanting to make that connection for you. So in the notes preceding this, you will have read a little bit about permutations. I don't want to get too bogged down in the permutations formula. We've actually talked about permutations without calling it permutations in the previous example. Well, a permutation is when order is significant in the organization of objects. So how many permutations are there of all the letters in the word Rio? Well, Rio itself has 3 letters. So there are 3 options for the first letter. Once one of those has been selected, you're left with 2 options. And then, of course, you'll have no choice about what the last letter is. So, as we have seen in the previous example, 3 factorial is going to be our solution here. And by now, you've probably made the connection and realized that actually 5 factorial and 8 factorial are your answers for those other questions. As we move on and take a look at the next example, we want to determine how many arrangements there are of 2 letters when they are selected from the word golden. I'll do the first one for you, and then ask you to have a go at the next 2 yourselves. So we have 2 spots that we need to fill. In golden we have 1, 2, 3, 4, 5, 6 letters. So the first of our 2 letters could be 6 possible different options. And then we have 5 possible different options for our second letter. You can work that out directly as 30. Just be aware that in factorial notation it would be 6 factorial over 4 factorial. I'll pause for a second and just double check with you to see how you get on with the next 2. Okay, hopefully you came up with the following answers. Take a moment to just pause again and read through the next section of the notes, and then we'll meet again at the following example. Okay, the previous set of notes is quite heavy duty, so I'm hoping you spent a little bit of time taking a look over that. If there's things that you're not sure on, we need to clarify that in class next time around. If we want to find the number of permutations of the letters in the word Vancouver, the first thing we want to do is identify how many letters actually are in Vancouver. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that we've got, normally, if all those letters were different, 9 factorial different options, 9 different spots that need to be filled. However, if we take a closer look, we can see that actually there are some repeats. Let's just double check. So the letters V repeat. So we're going to just divide through by 2 factorial there. When we look at the word mathematical, we can see that mathematical has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters there. Take a moment then to just go ahead and double check and see how you would approach this particular problem. So hopefully you realize that you're going to be starting off with 12 factorial as we've identified here. And then of course you've got several letters that are repeating. You've got the M, and so you're going to divide through by 2 factorial here. You also have the T identified here, and that repeats twice, so another 2 factorial comes in on the denominator. And then the letter A you're seeing 3 times. So overall you've got 12 factorial, 3 factorial, 2 factorial, 2 factorial. Certainly expect something like that to come up on future assessments. Alright, pause and have a go at the next example and we'll talk it through together. Okay, this one's always a little bit tricky. So part A is very, very similar to the previous examples. The word poppies has 7 letters, so we have 7 factorial. But of course, 3 P's are in the word poppy, so we're going to divide through by 3 factorial. So part A should be relatively straightforward. If we know that each arrangement needs to begin with a P, then we've got no choice about what that first letter is, so it's just going to be 1. And we're really just thinking, okay, how do we organize the remaining 6 letters? Well, there are 6 factorial ways of organizing 6 letters. Seeing as we have 2 of those P's still amongst those 6, we need to divide through by that 2 factorial. Okay, with part C, it's the same sort of idea. Again, we know that the first 2 letters are P's. If you take a look at the remaining 5 letters, there's no repeats in those remaining 5 letters, so we've just got 5 factorial. Now, with part D, things are a little bit trickier. If all the P's are together, then we can just treat the P's as one single object. All right. And so if we treat the P's as one single object, we're really actually organizing not a grand total of 7 objects anymore. All the P's together is one object, and then we've got the remaining 4 letters to organize, meaning in total we've got 5 objects. So if we're organizing 5 objects, we've got 5 options, 4 options, 3 options, 2 options, 1 option. Hence, 5 factorial. That one is a little bit tricky. And as a little bit of advice, we're lucky this time, all of the P's are the same type of object. What would happen if we were organizing, grouping together a collection of different objects? That's something that's worth thinking about looking into, quiz 1 and quiz 2. All right, part E. If the first letter is a P and the next letter is not a P, then you can see that we've got obviously one option here. If we now have 4 options that are not a P, we've got 4 options for letter 2. And then, of course, we've got the remaining 5 letters that need to be organized, so hence 5 factorial. Remember, of those remaining 5 letters, 2 of them are P's, and so we need to divide out 2 factorial to account for those P's. All right, in the interest of time, we're going to move really, really quickly. For example 8, you're going to have a quick go, pause, and identify whether or not it's a permutation, meaning order does matter, or it's a combination in which order doesn't matter. Have a quick go, and then check your answers with me on the next page. Okay, here are the answers that you should have had. I'm not going to go through each of these on a case-by-case basis, but if there are things you're unsure of, let's make sure we check in with one another next class. The final example today is something that you are definitely going to see a lot happening on our assessment. So pause, have a quick go, and we'll talk together. Okay, as you're having a go at this, the key idea really is that order is not significant. You don't care about the order in which the cards come into your hand, you just care about what's in your hand. So how many different 5-card hands are possible? Well, there are 52 cards, and you want to choose 5 of them. So that's going to be 52, choose 5. In how many of these hands will there be all diamonds? Well, out of the 52 cards, we need to choose... Sorry, my apologies. Out of the 52 cards, we're not choosing 52 cards here. Out of the 13 cards that are diamonds, we need to choose 5. Pause and have a go. All right, cross-reference your answers here. I think some of the ones that are perhaps a little trickier to get to grips with are things like the 3 kings. So the first thing that we need to do is actually go ahead, and out of the 4 kings, we need to choose 3 of them. We can't afford